So today's presentation will be about flow, and flow, as you probably know, is it's the name of our visual scripting language, which I've illustrated here with ASCII art. So it's a visual scripting language. It's based on, it has two core concepts, which are variables or arguments, parameters, and events. And it's based on a node graph. So in this node graph, you sort of create boxes that represent specific actions, and then you connect events and arguments in these boxes together. So in this case, I've illustrated this with a small graph here. We have a level loaded node with just an out event that gets triggered when the level has been loaded. So this is something you can use to initialize stuff in flow from flow. So that out event is then connected to another flow node, which means that when this event happens, when the level has been loaded, it will trigger this event in this flow node. And maybe I should make a clearer distinction here between the events and the variables, so it's a bit more clear. So this node, the spawn unit, this is a spawn unit node used to spawn a unit in the world, and it has, as you can see, it has two input events, one that will spawn this unit and one that will unspawn it, remove it from the level. The unspawn event here isn't connected to anything, so that one will never be triggered. So this unit will never be unspawned through flow. But the spawn event is triggered to this out event here. And then this node has two out events in turn, one spawned out event that might be connected to something else here, and that will be triggered after the unit has been spawned. So the in event will come in here on the spawn connector. The node will do its stuff, which means it spawns the unit, and then once the unit has been spawned, this out connector will be triggered. So then some other node could take over and do something with the unit that we just spawned. So the sort of execution flow in the flow graphs flows through these event connectors. Then we have variables. So these variables or arguments or parameters or whatever we call them are used to control what this node does. And this spawn unit has unit type, position, and rotation. So unit type is the type of unit that will be spawned, and it's connected to a node that supplies a string that just specifies that we're spawning a unit called large. So then that's the unit that will be spawned. The position and rotation connectors aren't connected, which means we will spawn this in Origo with default rotation. So in a real world example, these would be connected to something, but just for illustration here, they're unconnected. Then we have an output variable too, which is the unit that we just spawned. So after this has done its thing, this unit here will reference this unit we just spawned, and other nodes connected here might use that. So in a sense, this is a bit like a function. This is like a function with input parameters, output results, and these can be considered a bit like enums specifying what the function should do. Like it's functions that can do multiple things. So that's basically what a flow looks like. Of course, in a real world situation, it would be much more complicated with lots and lots of nodes. And the design goals behind this system, well, the purpose of this system, of course, should begin by saying, was to expose sort of the powers of programming, because programming is very powerful. It allows you to configure things in really dynamic, interesting ways, and make things that sort of the creator of the tool didn't really predict. So programming is super powerful, but not everybody is a programmer, and writing actual program code is not something that a lot of people are used to. So the design goal, the reason for having a visual scripting language at all, is to give that power, the power of programming, to people who are not necessarily programmers. So to put them in an environment where they won't get any syntax errors, they won't get any runtime errors or crashes, and they can sort of see what's going on, but still they have access to some of the tools of programming. Not all of the tools. A visual scripting language is still very restricted compared to like a regular scripting language. You typically don't have the same power of abstraction, of creating functions and variables and so on. And it also tends to be, it's kind of easy to read for small examples, but the more complex your code becomes, the harder it becomes to read. You can sort of end up with visual spaghetti if you try to do too much in the scripting language. So our philosophy is we shouldn't really force people to use the scripting language, the visual scripting language. We have Lua, like a regular proper scripting language where you can do the things needed for doing complicated stuff, and which honestly is a lot better at doing complicated stuff than the visual language. But the visual language is there to set up simple stuff and to give non-programmers some of this power. So that's a reason for this. For having this system at all. Some of the design goals. One of the design goals is that we shouldn't pay sort of a static cost for having this system, and that's the same design goal that we have in all of our system. I've said that before. You shouldn't pay for stuff that you don't use. So a flow graph shouldn't cost anything unless something is happening. So there shouldn't be like an update function that sort of goes through all the nodes and does something every frame. We should only execute code, we should only pay the execution cost when we actually have events being triggered. So when this out event is triggered and this spawn event is triggered, then something happens, then we pay the cost of execution. But just having the flow graph around and it shouldn't matter if we have 10,000 nodes in this flow graph, as long as they don't get triggered. There shouldn't be like any overhead to having nodes that aren't run in the graph. So that was a design goal. Another design goal, also shared by a lot of the code, is to have this sort of data-oriented approach, to not store this in a graph with 1,000 pointers to 1,000 heap allocated nodes, because that will always be super slow to run on modern hardware. So we want to be able to store this into single memory blocks rather than having these big graphs. So compile it down into memory blocks, and also for the resource, and also for the whatever runtime data we need. For example, the unit here will be set at runtime, and that data too we don't want to allocate as 1,000 individual heap allocations. We want to have this nice block structure for that data too. We want this to interface with Lua, because we still see Lua as the main programming language. So it should be possible to call into Flow from Lua and call out to Lua from Flow, so that you're not stuck in either of these worlds. And we also want the system to be extensible. This was added rather later with our first design of this system. That was before we had support for plugins and stuff like that. So the only way you could extend the system was either through Lua or by modifying the source code. There was no other way of extending it from the C side. But now that we have the plugin system, we've also made it possible to extend the flow system through plugins, so you can create new flow nodes in C. So let's dive a bit into the implementation. How is this system implemented? How does it work behind the scene? When we compile the data, as I said, the goal is to compile the data into binary blobs. So we have white box, I guess call them binary blobs, kind of the same thing. So a flow graph compiles into two binary blobs. One represents resource data, so that is static data for the flow graph, and that will be constant throughout the entire execution of the flow graph and not be modified. And then there is runtime data, and that's data that is modified and during the execution of the flow graph. So the unit reference here, for instance, would be in the runtime data. Now the runtime data, we will actually put that data in the resource too, and we will put the runtime data initialized with its default values into the resource. So we might have things here that have original values, like the unit here will be a null reference to start with, for instance. So we put that in the resource as well, so that we have a template for the runtime data. And then whenever we want to create an instance of this flow graph, we just make a new copy of the runtime data. And we can have multiple instances of the same resource running. We just make multiple copies of the runtime data that belongs to that flow graph. So let's look at an example. Let's look at compiling this spawn unit node, which has these three inputs: unit type, position, rotation. Then it has performed some spawn unit action, and it comes out with a unit pointer. Actually, it's a unit reference rather than a pointer. The weak references that I talked about before. So in the resource data, this node will look something like this. We'll first have some identifier that identifies this node as a spawn unit node. It's actually just a hash of the name of the node. And then it has all these input parameters are stored. So the unit type, but it's stored as an offset. So the type here isn't stored. The type here isn't stored directly in the resource data, and the reason is that the type isn't static. The type comes from some input here. Well, in this case, it happens to be static because it comes from a string node here. So we could theoretically do some constant folding or simplification of this and find out that this is actually static and could be stored in the node. But we don't do that kind of optimization on flow graphs. Also, it would make it kind of messy, because it would mean that in the resource here we would sometimes store like static data and sometimes we would store runtime data. So we don't do that. Instead we store instead we assume that all the data that comes on the input here comes from the runtime data, because it's connected to some other node that supplies this data at runtime. And it might be, in the typical case, it might have different values at different times of the execution, because it might come from some other flow node and be computed in some way. So instead of storing the data directly, we store an offset, and the offset is the offset of where we can find this data in the runtime blob. So somewhere in the runtime blob, is the representation of this string node here. So say that is node 2, for instance. Then the runtime blob will contain this string here in the runtime blob for that node. It will be compiled as part of this data, and then the unit type here will just reference that data. Same here for position. It's stored as an offset somewhere in the runtime data. We can find that position. Rotation somewhere in the runtime data. So all the data, all the parameter data, all the data that is on these like variable wires here gets stored in the runtime data, and we refer to it through these offsets. Same thing with the unit reference. In the resource data, we put our output data, we put our data somewhere in the runtime block. So when we write the unit reference here, we write it to somewhere in the runtime data, and in the resource we just know the offset where we should write this. I'll go a bit more into this later, so hopefully it will become a bit clearer if it's confusing now. But then after all this sort of resource data for this node, there's a lookup table for the output events. So there's a lookup table for all these that is indexed by the index of the output events, so one for spawn and one for unspawn. And then there's just a list of which nodes are connected to this output event. You can have multiple nodes connected to the same output event, so this spawn event could have multiple things that it should trigger. In this case, it's just connected to one thing, but it could be connected to multiple things. So here we have a list of the nodes that are connected to each of the output events, so that after we've executed spawn unit here, we can look up, well, what node should we call after we've finished spawning the unit. Yeah, as I said, the variables, the wires here, are all stored in the runtime data, and we store them in the resource. We store them at offsets into where in the runtime data we can find it. The runtime data for this spawn unit node is just the unit reference. So when we compile a node like this, and compile the spawn unit node, we will reserve memory for our output variables in the runtime data. So as we're going through here, we have our compile functions. We compile each node in the graph, and when we get to compile this node, we say, oh, I need space. I'm going to write the variable, so I need space in the output data for this thing. So we look at the current size of the output data. That's the offset where this reference will end up, and then we just bump the size of the output data so that we've sort of reserved that memory for storing our reference here. Note that when compiling the node, we don't reserve any memory for these input data fields because we don't need to, because that memory will be reserved by the nodes that these input fields are connected to. So this string node here, it has an output variable which contains a string. So when we compile the string node, it will reserve the memory for this string and put it there. And when we compile this spawn unit node, we will just see, oh, this input field here, this input variable, it's connected to this output variable here. So we'll just store the offset of that output variable wherever it is into this resource here. So that's how we know where to find that data. So yeah, we find where the input variables store and we directly reference that location. Yeah, I said all this. And for unconnected variables like the position here, this isn't connected to anything, then we just store a null reference, and we represent that by an offset that is just int max. So OX FFFFFF, and that means that we have a position that isn't connected to anything. So when the spawn unit runs, it sees that, oh, position isn't connected, and it will use a default value instead of getting the value from the runtime data. So an interesting thing to note about this design is that there is no need to copy variables between the node. Like when we're running this spawn unit node, we don't have to copy the string output from here into the input here, because it's all referencing the same data. The data just exists once for each wire, and then when it's connected to an input, the input will just reference that wire. So we don't have to do a lot of copying, which is good. It makes the execution of the flow graphs more performant than if we would have to copy data back and forth. One thing though is that we will need 2 compile passes. So we actually, when we compile a flow graph, we actually do it twice. In the first pass, all the nodes will reserve memory for their output variables. So in the first pass, the string, we compile the string here, we reserve the memory for its output and store its offset, and the same here, reserve the memory for this output and stores its offset. And in the second pass, all the output nodes will have all the output variables will know their offsets. So in the second pass, when we process this spawn unit, we can look up, well, where does this variable come from, and what is the offset that was assigned here. So we do one pass to find the offset of these output variables, and then we do the second pass to do the lookup of the input variables and find the right offsets. If we didn't do two passes, we would have to sort of order this so that when we will make sure that this has to be compiled before this node. Actually, that wouldn't be enough, because we can have sort of circular dependencies on the variables. So we would have to be smart about how we did this, so that we knew what the offset of the things were when we needed them in the input variables. But doing it in two passes is really the simplest way of doing this. The output events, like spawn here, when we store this, we store the offset of the node that this is connected to, so in the resource data. So if you remember, each node will have some representation in the resource data. The spawn unit representation will look something like this. So the start of the spawn unit here, where we find the identifier, has some offset in the resource data. And when we store the list of output connectors for level loaded here, since it's connected to the spawn unit, we will just store the offset of that spawn unit's resource data. So that's how we store the event connections. So now that we know how everything is stored, evaluating flow is kind of easy. To evaluate flow, we're starting at some node. So we have an offset into this resource data that represents the node that we're currently evaluating. Might be the level loaded node here. So that's kind of in flow, that offset kind of acts as our program counter, like kind of. So you can sort of look at this, if you want to, as a bytecode where each node in the resource data here specifies like one bytecode instruction, if you want. But we have some offset that represents our current node. We read the node type. It's the first member always that specifies the type of the node. So we read that from the offset. And then we have a lookup table that lets us look up the evaluation function that performs the action of this node based on the node type. Then we call that evaluation function, and that evaluation function will perform the action of the node. So in the case of spawn unit here, it will actually spawn the unit, and then it will update any output variables. So the unit reference here, it will write the new, after spawning, it knows the unit reference, it will write that unit reference into this, into the runtime data at the correct location. And it fetches the input data, of course. I didn't write that up here, but the node evaluation function will also, let me write that, fetch input data, will fetch input data, because it has the offsets of all the input data. So it just looks it up in the runtime buffer and finds the input data that is stored at that offset, reads it out, and once it has, or uses default values if the input data is not connected, and once it has all the input data, it can perform the action and then write the output. After that is done, it can trigger output events. So if you saw, we have a list of connected output events here. So in this case, if we're spawning, we should trigger the spawned output event. So we just get a list of the offsets of the flow nodes that are connected to this output event, and we will call them one each of those in turn. And then we're back here again. We have an offset for one of these output events that points to a new node, and we continue evaluating that node. So we just proceed like that. And that's how we evaluate the flow graph. Defining flow nodes. The flow nodes are defined in flow node definitions files. And these are just JSON files that specify some data for the flow node. So it starts with some documentation. This is parsed and goes into our documentation system. And then it has information about the flow node, what it's called. This is mostly legacy stuff for backwards compatibility. But it has some UI information, because these flow node definition files will be read both by the engine and the editor. So the engine will read them in order to compile the flow nodes, and the editor will read them in order to know how to show this flow node visually in the flow graph. Specifies the inputs and their types, units, and events, and it specifies the outputs that can come from this flow node. All our standard nodes are found in the core folder, so that's sort of the folder that is shared between all projects. And the implementation of those flow nodes are found in the main source code. And the way we find the implementation is that we register these. We register the C function that, because we can't really put the C function in the definition file here. It needs to be compiled with the rest of the game. So instead, it's somewhere in the code, and it registers itself with the flow node, with the flow evaluator. So somewhere in the code, we register that this name, this type of flow nodes, unspawn unit, should be handled by, and then some C function that performs the actual action. But this can all be extended through plugins. Plugins can add their own flow node definition files, and the plugins can also do the registration required to register the evaluation functions for these flow nodes that are added by the plugins. So one sort of design question that can come up when you start thinking about this is that we have like multiple ways of doing gameplay right now. We have flow nodes doing this visual scripting. We have Lua. We have the C API, which allows you to write gameplay in C rather than Lua. And we have the plugin API, which is kind of similar to, it has some of the same, that's like functions for extending the engine, whereas the C API is more functions for defining gameplay. But these kind of are kind of similar, they do somewhat similar things. So one thing you might ask yourself is maybe they should all be merged into a single system to avoid duplicate work, because we're needing, like by having all these systems, we need to expose APIs through all these systems. So maybe it would be better to just do it once and everything would be the same. And we're kind of starting to do that. We're merging, or I should say we have merged, because that work is pretty complete. We have merged the Lua and the C API. So those are actually based on the same thing. Lua will always call, the Lua functions will not call engine functions directly. They will go through the C API. So both Lua and C can be used for the same kind of gameplay. We will probably make the C API and the plugin API sort of move them together. Because currently we have some things that have representations in both of these. Like the application, for instance, there's a representation of the application in the C API and a separate representation of the application in the plug API, which is a bit weird. So we'll probably merge these two as well going forward. All of these will be kind of merged. And then you can ask, well, maybe we should merge the flow nodes as well. So instead of having sort of this system, the flow nodes should just directly be the C functions in the C API. So it should just be regular C functions and then just some graphical way of calling them. So there are advantages and disadvantages to that approach. I think that the way we design the flow nodes right now, we sort of define them or create them in a way for them to be simpler to use in a visual programming sense. And if we just use the straight C API, I don't think flow programming would be as nice. It would feel like more low level, and it would be harder to grasp for non-programmers. On the other hand, we're paying a lot of overhead by creating all the flow interfaces separately from these interfaces. So yeah, this you could argue either way. I think since we've already sort of started down the path we're on right now, where the flow API is quite different from the C API and more like novice user friendly, I think we will most likely continue on that path because we see value in having a simpler programming model compared to the C API model. So I think we will continue down that part, but it's something that you could argue either way. Going to go into a bit more special nodes. There's a special kind of nodes that are called query nodes. So a query node is a node that doesn't have any input events or any output events. So it just fetches data. It doesn't perform any action. And actually the sort of string node here is one of those nodes. The string node here doesn't have any input event, doesn't perform any action. It just provides this string. So it just provides data. And there are other nodes that do similar things. Where did I go? Yeah, there are other nodes that do similar things. For example, a node for getting the position of a unit. You don't have to trigger that node to actually fetch the position, because that would be kind of annoying if you would have to trigger all these nodes. Instead, these query nodes are triggered automatically. So whenever they're connected to something and whatever they're connected to needs to run, it will trigger all the query nodes that are connected to it. So it will sort of fetch the data from these nodes automatically without having to explicitly trigger an event to get the data. So the way this is implemented, a node stores a list of all the query nodes that are connected to its input variables. So if we had a get unit position node connected to spawn unit, a spawn unit would store a reference that it needed to run the get unit position node before running that node. So before the node runs, it triggers all these query nodes. So if we had a get unit position node connected, we would trigger that node. That node would evaluate, write the current unit position onto the wire, and then we could read back that information from the wire when running our node. So this is a simplification so that for situations where a node represents some data that is sort of dynamically changing and not an action that is triggered by an event. Another important thing to know about when it comes to flow is that we have multiple levels of flow. So the typical case for flow is that you add the flow as part of a level, so that in the level editor, as you create the level, you define a flow that might contain stuff like if the player goes over here, this door should open, and kinds of scripted behavior like that. But in addition to flow for levels, we can also have flows for unit and entities. So if you have, for example, a door unit, you could have a flow that applies always to that unit, and that you would create that flow in the unit editor together with the unit. So that might contain some logic for opening the door, for instance. It might contain a trigger that detects if someone is within a certain distance of the door, and then the door will open automatically. And if you have this in a unit, then every unit that you spawn, every copy of this unit that you spawn will have that flow. So all the doors that you place in the level will get the flow functions for opening the doors. And each of these instances will then have its own copy of the runtime data, because they're kind of separate execution contexts. We can connect and call between these different kinds of flows. So the level flow can, for instance, call into the unit flow. So the unit flow exposes external events and external variables for input and output. So in the case of a door node, of a door unit, instead of having the door automatically, instead of having a trigger in the door that opens the door automatically, the door could just expose an input event that is like open door. And then that could be connected to whatever in the level flow, so that the door was opened when the player stepped on a pressure plate or picked up a key card or whatever. So if we have these kind of external events and variables defined in the unit flow, whenever we place a unit of that type into the level flow, we will get a flow node which has like connectors for these input and output events. So in the case of the door, we would end up with a flow node that is called level unit, because it represents a unit in the level, and it would be connected to a specific unit, which is the door, and then it would have an input event corresponding to the external event defined in that unit's flow. So it might be called open door, for instance. And it would have other stuff here too, like the unit reference and so on, but I just don't want to type too much. But it would be something like this. So then you could connect other events in the level to this specifically defined open door event. So in this way, flow can sort of be extended with specific behaviors for units. You can create suitable events for the kind of behaviors that your unit supports, and then use those events in the greater flow. So this is kind of an abstraction mechanism for flow. There's also a general subflow mechanism, and not tied to units, where you can create a flow, like a freestanding flow with inputs and outputs, and then use that freestanding flow as a single flow node in a level flow or a unit flow. So another kind of abstraction mechanism. An important thing to notice here is that while we're in the same flow graph, like we're in this flow graph, then the data on the wires here are shared, so we don't have to do any explicit copy of the data. As I said before, we just reference that data wherever it exists in the runtime data. Now, if we have data in different flows, like maybe this level unit here has a variable that says how fast the door should open, called speed. Now, inside the unit flow, we cannot reference the level flow because this unit might be used in several different levels, and there's no way for us to store a permanent reference to the input data that is connected here. So in this case, when we're calling between different flows, we actually do have to copy the data. So we have to take some care when calling into subflows from a parent flow. We have to take some care of copying the data before we enter into the subflow here to evaluate this function. And the same goes for output data. If this has some data that it can output, that data needs to be copied from the subflow out onto this wire in the parent flow when we exit the subflow. So there's some explicit code for this in the flow evaluation. That's good to know about. I think that we could clean up the way you create external variables and events in a subflow. I think it's a bit messy right now. Currently, the way you do it is that you drop a node into the subflow that is called external input event or something like that, and then it will become an external event. But I think we could clean that up a bit, and maybe have just one node representing all the input data for subflow. But yeah, something for the future. But I think it's a bit messy the way we do it right now. Another useful concept that comes up in the flow code, that's good to know about, is trigger context. So in the spawn unit example here, I'm scrolling back up to this graph all the time, but just to reference it. In the spawn unit here, you see we have no input parameter representing the world, but when we spawn a unit, we always spawn it into a specific world. So you might then ask, how does the spawn unit know which world to spawn the unit in? How does this node know where the unit should be spawned when that's not an input parameter? The answer is that when we run the flow nodes, we run them in some kind of trigger context. It's called a trigger context. It could be called flow context or whatever, but it comes from, it's the context in which we first triggered something in flow. So, and this trigger context, it contains a pointer to the flow resource, so we know the resource that we're executing. It contains a pointer to the runtime data so that we can look up these input variables. But it also contains information about what unit we are running in for unit flow, what level we are running in for level flow, what our current world is for world flow, or what entity we're running, if it's an entity flow. So can look at that here. We have somewhere here, we have the trigger context. Yeah, so it's just a struct with all the necessary data here. This is the flow resource, static data. This is the dynamic data for the current instance that we're executing, our unit, our entity, and so on, the world, the level. Some information there. One thing that needs to be handled carefully, and that you will see some special code for again in the flow execution, is that when we are stepping into a subflow or stepping out of a subflow, we need to update the trigger context so it represents properly the flow we're currently in. So when we're calling into a unit flow, we need to set this unit pointer because to the unit that we're currently executing the flow for. And at the same time, when we're stepping back, if the unit flow exits and we get back to the containing flow, then we need to make sure that the resource data points to run thing, the runtime data points to run thing, the unit shouldn't be set anymore because we're no longer executing in a unit flow, and so on. So there's some code for handling this, and this is again a bit code that is a bit easy to mess up. So if you forget to copy some field here, things will start behaving weirdly. So it's a good thing to know about that we need to take care of this. So I want to say a little bit about events, and this is not specifically about flow events, about events in the engine in general. As I talked about before, we have events coming from physics, we have events coming from animation, like trigger events in the animation, collision events in the physics. And we've sort of decided in the engine that flow should be our main mechanism for dispatching these events. And so we don't generally allow registering event callbacks through Lua or C APIs. It always has to go through flow. And you can discuss this as a design choice. I know some of the people who mostly spend their time in Lua or mostly spend their time in C, writing their gameplay in Lua or C, are kind of annoyed that in order to be able to handle events, they have to create flow graphs and stuff like that. The reason we did it this way is kind of our experience from previous engines that event system can become kind of messy, especially when you have sort of a multi-dispatch system that events can come in from anywhere and go out to everywhere. It's kind of really hard to follow what happens in the engine, like who calls who, where does things end up. And it can also create a tight coupling between different systems. If an event in animation directly calls out to sound, for instance, that sort of couples those systems. The sound events become dependent on what's happening in animation. So our goals were like, we wanted to have all events being processed at the highest possible level to avoid the situation where if animation calls out directly to sound, then that might happen when animation is kind of an intermediate state, like in the middle of the animation's update function. And then you can get really nasty bug if the sound, if this callback triggers some event that triggers another event that callbacks into the animation system. And now we're trying to do something in the animation system while we're in the middle of the animation system's update loop. And that can create really, really troublesome bugs. So we wanted to make sure that we're doing all the event processing at the highest possible levels. And we also wanted a single system for dispatching the events. So it wasn't that, well, they can sometimes go to Lua, sometimes go to C, sometimes they're processed in Flow. We wanted it to be clear where events are processed. So we were like, well, it's all going to happen in Flow, and then you can connect it to other stuff. If you want to call out to Lua, you connect it to a Lua node, or if you want to call out to C, you connect it to a custom node. So that was kind of the main ideas behind that design. I don't know if it's totally the best choice still. I'm kind of thinking that allowing registration of Lua or C callbacks would be a good thing. I think we should still have the approach that we always process events at the highest level. So we should still process the events in the world. We should not directly call out from low-level system, because that creates these crazy couplings and these crazy bug-prone situations. So we should still do all the polling and all the handling of the events at kind of the top level. But I'm kind of thinking that it wouldn't hurt to have support for direct Lua or direct C callbacks, and it would kind of make life easier for people who don't care so much about flow. So, but something to think about for the future. So an example of how the event system works today is, let's use physics collision as an example. So when we compile a unit file, we check for each actor in the unit, so each physics actor in the unit, if it has an on-collision flow node. So we look at the flow for the unit when we compile it, and we sort of go through all the flow nodes that have to do with actors and see if there is a flow node that wants to react to collisions with this actor. If we find such a flow node, we store an offset to that flow node in the actor resource. So the actor knows how to call out in the case of a collision. Then in the physics world, we have general callback for processing collisions. When we get a callback that a collision has occurred, we check the involved actors in the collision. We check if any of them has an offset set for an on-collision event. If not, we drop the event right then and there, because there is no more processing to done for that event. And that's a useful optimization, because there might be a lot of collisions in physics. But if one of the actors, either of the actor, has an on-collision offset, so it wants to react to collision event, we push that event into the output event stream for physics. And as I said in the physics talk, that event stream, it's just a buffer, it's just a big buffer where we push the events one after another. And then we process these events at a higher level in a world, And in world, we look up the flow event for these involved actors, and we then trigger it. So we call into flow to process this event. So this is our general event handling mechanism. It works with events from animation, from physics, from particle effects, and so on. This is our general system for handling events. Another node that has kind of a special processing is the delay node. The delay node will get an input event and then wait a certain number of time and then trigger its output event. And since we don't want to have a general update in flow, as I said before, we don't want to check every frame with these delays for these delay nodes. Oh, should you trigger right now? We don't want those kind of updates. It shouldn't cost anything unless events are happening, as I said before. We instead handle these by letting the world keep track of delayed triggers. So the world has a sorted array of delayed flow events and the time at which they should trigger. So each time we update the world, we sort of check the head of that list and see, oh, should some delayed flow event be triggered now? And if it should, we trigger that event. So that's the main implementation of these delay nodes. We need to take some care so that we delete these delayed events if the flow that owns them goes away. So if the unit, for example, is deleted, we shouldn't trigger a delayed flow event into that unit's flow because that unit's flow won't exist anymore. So this is all handled in the world update. Final thing I want to mention about flow is that we have support for what we call script flow nodes. So in addition to defining new floats in plugins, you can also define new nodes in Lua. So the sort of Lua gameplay programmers can extend the flow interface and create new nodes for the level designers or artists to use. So it's kind of a nice way of getting a good collaboration between the gameplay programmers and the artists. The artists want to use the high-level visual scripting system, but it might not have the functionality that they exactly need. Then the gameplay programmers can extend it through Lua and provide that functionality. So the script flow nodes are defined in the project in script flow nodes files, which are just JSON files that look kind of similar to the flow definition files. They have documentation if you need that, and then they have some description for this. This is information for the editor so that the editor can display these flow nodes in a nice way. And then you specify the arguments, the output variables, and the Lua function that should be called. And the way this works is that the input and output arguments will be gathered by the flow system using just the same mechanism as if we executed a regular flow node. We'll fetch the input arguments from the wires, and then we will set them up in a Lua table. So all the arguments will be put in a single Lua table, which is indexed by the name of the variables. And then we call this function, this Lua function, with that table as an argument. So we will call that human IK switch on and just pass in that table. The Lua function will read input from that table, write any output variables to the same table, and perform whatever function it needs to perform. It's also possible to write the code directly in here if you don't want to be dependent on loading this Lua function from some other Lua file. You can also write Lua code directly to execute inside the node, which is useful for some situations. That's basically it for flow. Are there any questions on this? Yeah, we almost took the full hour for just flow, so good we didn't try to cram more stuff in. All right, so thank you. We'll see you. I'll take a break with these presentations because I'm going on vacation in GDC, but continue after that. So thank you.